Hi, my name is Joey Sleiman, and today's topic is an introduction to parallel computing. What is meant by parallel computing? Parallel computing is a type of computation in which many calculations or the execution processes are performed at the same time. It follows the basic principle similar to that of a divide and conquer algorithm, which means that computations can be divided into subproblems which will execute in parallel. A brief history of parallel computing. Surprisingly, the idea of parallel computation was present since the early days of computing. In the 19th century, an English mathematician called Charles Babbage invented the concept of a programmable computer called the analytical engine. Then, an Italian general and mathematician Luigi Manibrea formed a sketch of the analytical engine and envisioned an extension in which independent computations were performed simultaneously. In the 20th century, researchers from IBM, John Koch, Daniel Slotnick, and Jean Amadale built some of the first commercial parallel computers. As we can see here, to the left we have Charles Babbage, and to the right we have Luigi Manbrea, and in the middle we have the analytical engine which Charles Babbage described. Why did the need of parallel computing arise? So when processors first came out, they had a certain number of transistors in them. Then companies aimed for better execution times and faster performance. In order to do so, they started increasing the frequency inside these processors. And by increasing the frequency, they started making the transistors inside these processors smaller so they can fit more into it. Eventually, they hit a physical limitation which is called the power wall. The power wall is due to hardware limitations current companies face, which is affordable methods for power delivery and dissipation. In other words, if they try to add more transistors inside the processor, they can deliver power to the entire processor, or they won't be able to deal with the power dissipation inside the processor. Also, the problem of heat arises with such number of transistors. So if they increase the number of transistors beyond a certain point, they won't be able to deal with the heat emitting from the processor, which can cause the processor to either burn or melt. And that's why companies such as Intel decided instead of scaling a single processor, they will use more than one processor at the same time. Common misconceptions. Parallel computing is usually thought to be similar as pipelining, although both processes involve the execution of multiple instructions at a given time. Parallel computing differs vastly from pipelining, which we will see in a moment. Parallel computing is also mistaken with concurrent computing. Parallel computing is closely linked to concurrent computing. They are frequently used together, but the two of them are different. In parallel computing, a computational task is usually broken down into several very similar subtasks that can be processed independently and whose results are combined upon completion. On the other hand, in concurrent computing, the various processes often do not address related tasks. Now let's discuss how parallel computing actually works. Over here we have our basic processor where we input instructions and the processor is going to execute these instructions through the 5 stages we know: instruction fetch, instruction decode, execution, memory access, and the write back. Now, if you're using pipeline, these instructions will enter through the pipeline, and eventually the pipeline will fill up. Here we'll have the first instruction, here we'll have the second, here the third, fourth, and the fifth. Okay, and after the first instruction is done on the write back stage, the instruction will be done with execution and will go out the processor. Now for parallel processing, it's the same concept followed here, except we won't have a single processor. We can have two processors and sometimes four processors. Now let's say we have two processors. It will take in the instructions, but it won't take them in into a single processor. They'll be divided into two processors as follows. As we can see, the instructions are divided among two processors, and if these processors were also pipelined and the pipeline were to fill up, we'll have as follows: instruction 1 and instruction 1, instruction 2 and instruction 2, 3 and 3, 4 and 4, 5 and 5. As we can see over here, that we'll have two instructions instead of one at each stage. Now, going back to the fact to the part where we discussed the difference between pipelining and parallel computing, it is evident from this figure over here that pipelining Although it executes multiple instructions at the same time, it's different from parallel computing since parallel computing executes multiple instructions at the same time but across two processors instead of one. So in parallel computing, we can actually use pipeline to even make our processors go faster. We have four types of parallelism. The bit-level parallelism, which means we execute bits in parallel. An example of that is when we want to add 16 numbers and we only have 8-bit registers. In order to add them, we're going to have to add the lower 8 bits together and the upper 8 bits together and then concatenate. But the addition of the lower 8 bits and the upper 8 bits will be performed simultaneously, not one after another, which differs from the sequential computation. Then we have the instruction level parallelism, which we discussed earlier, and we have the task level parallelism. Task parallelism is basically when we have two different programs running. One program instruction will be run through a certain core or processor, and another program's instruction will be run through a different core or processor, but both instructions, even though they're independent and do not relate to one another, they run at the same time. Finally, we have the superword level parallelism. What is meant by this? Now, this can be explained through an example. We want to have this for loop run on less iterations. So what we're gonna do is we're gonna vectorize it. In order to do that, we're gonna have to use a process called unlooping, which is common for superword level parallelism. Unlooping the for loop, it means we now, as is shown in the figure, the next step is going to be executing 3 instructions instead of 1 per iteration, which will decrease the number of iterations needed. But these 3 instructions won't run one after another. These 3 instructions will be run in parallel. So now we can say that the area A is a kind of vector and the area B is a kind of vector, hence the name vectorization, which we can see now in the final part of the figure. Parallel hardware. We have the multi-core processors, the symmetric multiprocessors, the graphic processing units GPU, field programmable gate arrays FGPA, and the computer clusters. As we can see in the figure over here, we have our multi-core processor. It has cores inside a single processor. Then we have the symmetric multiprocessor. What do you mean by that? It means we have symmetrical processors, as in similar, and these processors can also have multiple cores. These processors are linked to memory via a bus, and we also have the GPU and the FGPA, which are co-processors. The GPU is a graphic processing unit, which deals with instructions related to graphics and such, which, in other words, it doesn't necessarily execute all instructions given by a user. It executes instructions that are forwarded to it from the main processor. We also have the other coprocessor, the FGPA, which can be rewired or reprogrammed for multiple uses using the programming languages of HDL and Verilog. Finally, we have the computer clusters, which are connected to the memory via a LAN. And these computer clusters can either be connected to the same memory or can be connected to different memories. And each of these computer clusters can have its own GPU and FGPA, making them heterogeneous computer clusters. But these computer clusters, as everything defined earlier, run in parallel to one another, which helps speed up execution time. Usage of parallel computations. We have smartphones, such as the iPhone 5, which uses a 1.5 gigahertz dual processor, and the Samsung Galaxy Note 10, which uses 8 processors. The laptops and desktops, which use processors such as the Intel Core i5 and the Core i7. NASA Space Shuttle Computer System, which constitutes of 5 IBM APA-101 computers running in parallel. American Summit Supercomputer, which is the world's leading supercomputer, and then can execute 200 quadrillion instructions in 1 second. A fun fact is that if you get every single person on Earth and let them execute 1 instruction per second, it will take them 10 months to do what this supercomputer can do in 1 second. Then Bitcoin. Bitcoin runs on blockchains for transactions of money and currency and such. So, and blockchain depends on parallel computing. So if we were to use sequential computing, blockchains couldn't be implemented and Bitcoin wouldn't have been developed.